Hey everyone, this is Mr. John McGinnis here with an AP Calculus BC video on the shell method for volumes using integrals. Before this video even starts, I advise all of you to not grab a healthy snack. Don't eat anything while you're watching this video, as you'll probably just attract a bunch of ants, because that's how these rooms are. Um, don't even use the microwave to drink tea if you're freezing. It's best to do math when you're very cold, studies have shown. Additionally, no fidgeting, no fidget spinners, no nothing, because you can't spin and listen. That's what they say. Okay, so let's get into the video. So first, I'm just going to start off with an example here. The question is, calculate the volume of the solid formed by revolving the area between the curves y equals 0 and y equals negative x plus 1 about the y-axis over the interval for 0 is less than or equal to x, which is less than or equal to 1. So we're going to be calculating a volume here by revolving an area bounded between technically three curves. From 0 to 1. So why don't we draw a picture here first? So we'll just sketch. This is just the xy plane, and I've sketched in blue here y equals negative x plus 1. So basically what we're going to be doing is we have this line here, and we're going to take this area and the curve y equals 0. So we're going to take this kind of triangle here. From 0 to 1, we're going to revolve this around the y-axis along x equals 0, and then we're going to calculate this volume. So you guys did this in geometry with Mrs. You-Know-Who back in geometry. We keep referring back to that course in this class. This is really just a review of everything that you've already learned, but it gets tricky because you have to do everything at once. Okay, so we're going to be taking a cone here when we revolve this triangle, this right triangle, about the axis. So back in geometry, to solve this problem, you would have used the fact that the volume of a cone is equal to 1/3 base times height. Of course, the base is going to be pi r squared because the base of a cone is a circle. So we're dragging this point from we're dragging this 1, 0 point here to negative 1, 0. And you can kind of imagine that we got this big cone going on here. So like a 2D view of it would probably look like this triangle this isosceles triangle here that I'm drawing out with the red laser thingy. Yeah, and then you can just solve. We know that the radius here is going to be 1, and that the height here is going to be 1, because our equation is y equals negative x plus 1, and those are just the intercepts. Yeah, and then this is just going to equal pi over 3. However, this is, of course, an AP Calculus video. You're in the honors class here, so we don't really want to just use the fact that the volume of a cone is 1/3 base times height. We want to use calculus to solve this. And we want to be thinking about questions like, why is the volume of a cone equal to 1/3 the base times the height? Where does that 1/3 come from? Okay, so we already have done definite integrals. We started that a couple of weeks ago, and we know that you can kind of partition. We're just going to do the same problem here. This blue line is still y equals negative x plus 1. And we're going to kind of divide it into infinitely many little rectangles with very small widths. The widths approach 0 here. And we have infinitely many of these, of course. And so if we were to calculate the definite integral of y equals negative x plus 1 from 0 for the limits from 0 to 1, then we would end up dividing this into infinitely many rectangles and using our knowledge of calculus, our knowledge of definite integrals, to calculate this area. Well, what we're going to do is we're going to kind of be clever with this, and we're going to actually divide this volume that we can imagine, like this cone again, that I'm kind of sketching out the cross-sectional view of. we're going to find the volume of this by breaking this cone up into infinitely many cylinders, hollow cylinders with a kind of a thickness of, well, a thickness that approaches a limit of 0. So we're going to be adding up these infinitely many little cylinders. And what we're going to actually end up doing is, since the thickness is going to approach 0, we're going to basically just be making a bunch of rectangular prisms. Okay? So if we think about what one of these little hollow cylinders, what the volume is equal to, well, the radius, kind of, not really the radius, but kind of like the thickness, is going to equal dx. Because dx, we're approaching 0 with this. We're adding up infinitely many. And then, of course, we're adding up infinitely many because, as you can see, when we only add up, what is this, like 10, 15, we have these small areas that we're missing out on. And we could overshoot it, but then we'd have too much area. So we have to add up infinitely many, and the limit will be the area. The height, of course, is just going to be y equals, well, it's bounded by this blue curve here, y equals negative x plus 1. So the height is, of course, going to be negative x plus 1. And this is the part that's kind of hard to understand. Well, we know that this is supposed to be an r here. So the circumference of a circle is equal to 2 pi r. And we can use that fact to find kind of the circumference of one of these little hollow cylinders. And I'll call that the length. That's going to be equal to 2 pi x. Because, of course, x is equal to the kind of radius of this hollow cylinder, and then the 2 pi because we're finding the circumference. So the circumference of this very, very, very thin, infinitely thin hollow cylinder is going to be 2 pi x. So I was talking about the rectangular prism. What we're going to actually end up doing, let's just look at one of these infinitely small rectangles for now. Let's look at this one. So we're going to be making a hollow cylinder with a thickness equal to dx, where of course the width of this rectangle is going to equal dx. And that's what we're going to get when we're going to revolve this infinitely small width box around, or a rectangle around the curve x is equal to 0. And what's going to really happen, if we think about cutting this hollow cylinder on one of its sides, kind of like if you roll up a piece of paper, think of it as a rectangular prism, okay? So the height here is going to be equal to this curve where we are at. This kind of thickness here is going to be dx, so this rectangular prism is going to be infinitely thin. And then we're going to have this, if we were to cut this cylinder and unroll it like a piece of paper, we would end up getting our length of our rectangular prism equal to 2 pi x, where that's coming from the fact that that would be equal to the circumference. If we were to cut this here and then unroll it, we would have this circumference there of the hollow cylinder equal to the length of this here rectangular prism. So for this, we have the width, the height, and the length. The width is going to be equal to dx because it's going to be infinitely thin. The height is going to be negative x plus 1. The height here is going to be negative x plus 1 because that's our curve. And then the length is going to be 2 pi x because for this little rectangle here, this little very hollow, infinitely thin cylinder here, the circumference is 2 pi x, so that's equal to the length here. And of course, we know that the volume of a rectangular prism is equal to the width times the height times the length, or the length times the width times the height. So we know that dV, this infinitely small volume of this infinitely thin cylinder, is equal to the length times the height times the width. And so what we're going to want to do here is take the integral of dv, which is going to be equal to v, and then we're going to get here, we're going to have to integrate this side as well if we want to solve for v. And this integral is going to be a definite integral, and it's going to have the limits x equals 0 to x equals 1, because if you look back at the original problem, we were finding from 0 is less than or equal to x, which is less than or equal to 1. So we can go ahead and start integrating this. First we'll multiply this kind of binomial. We'll distribute the 2 pi x into this negative x plus 1. We'll take out the 2 pi because 2 times pi is just a constant. And we're left with 2 pi times the definite integral from 0 to 1 of negative x squared plus x dx. And of course, this is just the power rule for integration. This is going to, well, this indefinite integral here, so ignore the limits for right now, would be equal to 2 pi times negative x to the third over 3 plus x squared over 2. But of course, we are dealing with a definite integral, so we're going to have to plug in here. We're going to plug in the 1. First, we're going to evaluate the indefinite integral at 1, and then we'll subtract the value of the indefinite integral at 0. This is no different solving this definite integral from if we were just to be calculating an area. So we'll get 2 pi times, of course, 1 to any power is just equal to 1, and 0 to any positive power is equal to 0. So all of this here, this negative 0 cubed over 3 plus 0 squared over 2 is going to be equal to 0. And then this is just going to be negative a third plus 1/2. Negative a third plus a half is equal to 6, or 1/6. 1/6 times 2 is equal to a third, and then a third times pi is just pi over 3. And we got the same answer from before. However, now we've basically shown how to find any volume revolved around the y-axis of a curve and the area of the curve and y equals 0. So we can get into a harder example here. Solve for the volume generated when the area between the curve y is equal to sine of x and the x-axis is revolved about the line with equation x equals 0 from x equals pi over 2 to x equals pi. Okay, so we can kind of think about drawing a picture here. We have this curve y is equal to sine of x, so we have like our sine wave. And then we can think about here, we're going to take that from the x-axis, so the area bounded by y equals sine of x to the x-axis. And then we're going to take that area and we're going to revolve around x equals 0, which is just another way of saying the y-axis. The y-axis is the curve such that x is equal to 0. And in the previous example, we were going from x equals 0 to x equals 1. Now we're going to go from x equals pi over 2 to x equals pi. So just like before, dv, that infinitely small area of that infinitely thin hollow cylinder, is going to be equal to the length, which is the circumference of that cylinder, 2 pi x, times sine of x. Sine of x is the height. It's equal to the curve. It's how high those infinitely thin rectangles go. And dx represents the width of the thickness of the hollow cylinder, or the width of one of those infinitely thin rectangles. That's going to be dx. And so this is going to be, if we just integrate both sides of this to solve for v, this v is going to be equal to, I'll just take out the constant, 2 pi times the definite integral from pi over 2 to pi of x sine x dx. So, looking at this right here, we have to basically integrate x sine of x dx. And the way to do that is going to be to use integration by parts. Now, we've already done integration by parts several weeks ago, so I'm not going to really get into it here, but I'm going to choose u equals x. I'm going to be strategic here. And then, I'm sorry, this is supposed to say du. Du is going to be equal to dx, which is going to be easier to work with later. And then I will use, since we have to go u and dv, I will say dv is equal to our sine of x here. And then if we integrate this, dv is equal to sine of x dx, we can solve for v, which is equal to negative cosine of x. Okay, and then we just use our integration by parts formula. The indefinite integral of x sine of x dx is going to be equal to negative x cosine of x, that's u times v, plus sine of x, where sine of x is equal to negative 1 times the indefinite integral of negative cosine of x dx, which of course the negatives will eliminate because well, we're just going to be minusing a minus, which is going to be the same as adding, and then the indefinite integral of cosine of x is equal to sine of x. So that's where we're getting that from. And now, since this is, of course, a definite integral, we just have to plug in here pi of this x sine of x minus pi over 2 of x sine of x. So you can just plug that in. It's going to be 2 pi minus pi cosine of pi plus sine of pi minus negative pi over 2 cosine of pi over 2 plus sine of pi over 2. And we can, of course, simplify this further. We know that negative pi times cosine of pi is just going to be equal to negative 1. So we're going to have negative pi times negative 1, which is just pi. Sine of pi is 0. Cosine of pi over 2 is 0. Sine of pi over 2 is 1. So we need to remember to distribute this negative here. We're going to end up taking 2 pi times pi plus 0 minus negative 0, which is plus 0, and then minus 1. So our final answer here is going to be 2 pi times pi minus 1, which is approximately 13.456. Now, I took this picture from Wolfram Alpha, and you can kind of imagine what we just did. So we have this curve, this sine wave right here, the top of a sine wave, half of a period right here. Y equals sine of x is in the blue, and then y is equal to 0. So we have this area right here, this cross-sectional area, from pi over 2 to 1, or from pi over 2 to pi. And then we have our x equals 0 here, our axis of revolution, which is the y-axis. And we're taking this area bounded by sine of x and 0, y equal both of them, and we're revolving it around. So we're kind of getting this weird shape, and we're taking kind of a cylinder out of it because we didn't go from 0 to pi, we went from pi over 2 to pi. So, and we added up these infinitely many rectangles, or these infinitely many hollow spheres, infinitely hollow, that went all the way around. And that's how we solved that using calculus. Okay, so before I end off the video here, we're going to have some to try on your own. Make sure that your homework section is very neat. I should be able to see all of the steps. Circle anything. For the next problem, I should see many, many, many things circled. And be sure, only use your red pen if something is wrong. Don't just mark it as correct. I know there's a bunch of you in here. And be sure to highlight your top. I have a system, and so our question for you to try on your own is, part of a nose cone can be modeled by the solid formed when the area bounded by the curves y is equal to 0.5x squared and y is equal to 18 is revolved about the y-axis. Using your knowledge of the shell method, so that's using some also call it the cylinder method because they're all of those hollow cylinders, so using those cylinders in calculus, compute the volume of this nose cone to the nearest integer. Now, the one thing that kind of makes this problem hard is you're going to be taking this area, and notice that this purple line here that's part of our area is not going to be y equals 0, it's actually going to be y equals 18. So think about what your height is going to be here. Your height is not just going to be 18 everywhere. Your height is going to be, well, you have to figure that out on your own. So just use the cylinder method, find your height using these equations. You can use this picture right here. I just got this from Wolfram Alpha 2. And we're going to be bringing it around the y-axis. Okay, so this will be due tomorrow. We have a quiz next week. It should be super easy, but you got to fly through that thing. You can't just get stuck. And have a good night.